Hi, everyone. Clinton Edwards here again in the second lecture in our series on planning your own large area imaging project. Now that we are starting to understand what we should and should not be using large area imagery for, let's think through how we might start planning our own surveys. First, we need to remember that the effort needed to execute each of the four main steps of the large area imaging pipeline, including image collection, model generation, data extraction, and management, all increase in effort with the number of images that we collect and the resolution of those images. The fundamental challenge then to address before you start your large area imagery project is how to balance your research goals with your resources. Striking this balance first begins by determining the resolution you need in your large area imagery products. For instance, if you require genus level data, your plan should allow you to reliably collect imagery at this level of detail at all your study locations. Similarly, if we are interested in robust site level estimates of percent cover, we must sample with enough replication to capture the variability at each site. Ultimately, the needed sampling effort in terms of the size and number of plots should be based on the ecological context of your study system, including the number and size of corals and other organisms, as well as how patchily they are distributed across the environment. Now, such decisions can be a bit of a two-way street. For instance, if you need genus level data, then there is no need to collect imagery with sub-millimeter scale resolution. However, if collecting more detailed imagery does not represent a significant increase in effort for you, it is always recommended to collect the most detailed information possible. Similarly, while you might be able to capture what you need in a smaller plot, if increasing the size of the plot does not represent a significant burden, doing so is encouraged as it will only provide more robust data. So let's consider some of the general categories of data that we might want from large area imagery and how our choice of these data streams might influence our decisions of image resolution and plot extent. If, for instance, you wanted to describe community structure or create population demographic models, you will need information on the abundance and size of organisms. The resolution of the model you will need will then depend on the detail with which you want to present your data. Maybe you want species level data, but work in a very high diversity system. In such cases, you will need pretty high resolution images like the one shown here to be able to get the taxonomy right. On the other hand, you might just need to be able to get to things into coarser groupings like genus or functional groups such as algae versus coral. And in these cases, much lower resolution imagery like this will be sufficient for your needs. Similarly, in some locations, corals are more abundant than in others, and adequate replication can be achieved with fewer and smaller plots. However, at places where corals are less abundant or more patchily distributed, more or larger plots may be required to achieve the necessary statistical power for your desired analyses. The next category of data we might consider requires spatially explicit descriptions of organisms. Many spatial analyses are based on colony position centroids, and while a relatively low bar in terms of resolution of large area imagery, the taxonomic resolution you will want to work at will instead drive decisions of resolution. Importantly, for any analyses that requires explicit descriptions of colony shapes, such as the nearest neighbor analysis shown in this slide, you will need detailed colony boundaries, and as a result, higher resolution raw imagery. Additionally, many spatial analyses require buffers around the core study area to account for edge effects. It is thus recommended to consider such requirements when designing your surveys. Finally, if you want to investigate structural complexity, your main requirement is a geometrically accurate model. As with all other analyses, the level of detail is ultimately dependent on the question you are asking. If, for say, we are interested in the effects of a ship grounding on a reef, as shown here, we can largely get the data we need from relatively low resolution models. But if you are instead interested in differences of complexity as a function of coral morphology, you will need a much more detailed model. And finally, when determining the spatial extent of your plots, we must consider the spatial scale of the structural features of interest. While plot sizes on the order of meters, like the one shown here, might be sufficient for looking at biological complexity responses, if we are interested in larger scale gradients in structure, we should use much larger plot sizes, such as the hectare plot scale shown here. Okay, with this, we should be ready to start making decisions about the size and number of our plots and how detailed we want our raw imagery to be. But now that we can make these decisions, we need to circle back to that fundamental constraint on large area imaging, which is that it always requires overlapping images that are well taken. Because regardless of how nice our camera is, if we don't use it right, then it won't take good pictures. So how do we do this? First, let's focus on overlap. It is important to have a way to navigate around the plot to make sure that you have covered the entire area. This applies no matter the scale or the imaging platform that you are using. Again, the most important thing is overlap, so you need to make sure that you have a way to achieve it consistently. This requirement gets harder the bigger the plot area is. In a small plot, a diver might be able to navigate their way around the plot by memory, while in a larger plot, visual markers such as temporary floats are highly recommended. For AUV or towed surveys, GPS navigation will almost certainly be required to ensure that you're maintaining good coverage of the entirety of your plot. An easy way to ensure that you've covered your area is to use a systematic approach, such as a grid or a spiral. Remember, the primary goal is simply to have overlap. In the plot on the left, the diver used a single set of long passes to systematically image the plot, while on the plot on the right, the diver used 2 sets of parallel passes. Note that passes in the second plot are much more closely spaced. There are many more of them and from different angles. It is not surprising, therefore, that the model on the left is incomplete, while the model on the right doesn't seem to have any reconstruction errors that we can see. While an image was generated in the model on the left without proper overlap in the interior, it suffered from relatively large reconstruction errors. To that point, you will also notice the ragged edges at the plot boundaries. This is an inevitability of large area imagery, as we have to stop taking pictures at some point. And as a result, the pictures on the edges will overlap with fewer other images, resulting in lower reconstruction quality at these plot boundaries. This also highlights that we need to ensure that we maintain a buffer around our core plot area to make sure that it is sufficiently imaged. As divers, we can do a number of things underwater to make sure that we keep swimming straight and image our entire area. Dead reckoning, or using features around us to create a mental map by which we navigate, is a simple solution that works in most cases. We can also deploy features around our plot, like the temporary floats at plot boundaries shown in the video here, that allow us to navigate and maintain a constant height above the substrate. We can even take advantage of standard dive equipment like a compass and depth gauge to help us keep track of our position in the surroundings. Such added tools are particularly useful in homogeneous environments where features look similar or where visibility is particularly low. Whatever method you choose, the goal is to maximize overlap and maintain consistent coverage across the entirety of our core plot. When it comes to maintaining overlap, equally important as our swim pattern is the distance we are from the bottom, as this also affects the spatial footprint of our imagery and thus the overlap between images. This is true regardless of the camera or lens type that we are using. Importantly, if we do not maintain consistent height above the bottom between passes, we risk that images from one pass will cover a much smaller footprint or different footprint than images from another pass, thereby making it harder to maintain consistent overlap. As you can see here, we have 2 passes where the diver was 2 meters above the bottom, and those 2 passes have a real high degree of overlap. However, the pass where the diver was just 50 centimeters above the bottom, here in yellow, does not overlap very well with even the pass where the diver was 2 meters above. This is because that diver that was swimming close was imaging a very small spatial footprint, and as a result, we don't have good overlap in this area, resulting in the reconstruction error that you see there. We must remember the caveat also that the further we swim from the bottom, the lower the resolution of our images will be. Similarly, a wide angle lens will produce images with a much larger spatial footprint, but lower resolution than images taken with a telephoto lens on the same camera. Again, the goal here is to encourage you to first determine the area that you want to image, as well as the detail you want to image it with, which remember are both functions of the biological or physical signal that you want to capture. Once you've made these decisions, you are then ready to balance your research objectives with the effort that it's going to take to accomplish those objectives. And then from there, you can make your final plan. Final note on swim patterns and overlap. Coral reefs are almost impossibly complex environments, and despite our best intentions, studying them in all their cryptic glory still poses significant logistical challenges. Luckily, physics and light are on our side. And even with a simplistic top-down imaging approach, wide-angle lenses on cameras have an astounding ability to peer into otherwise occluded areas. The image shown here is an Acropora palmata colony image with a mix of top-down and oblique imagery. By tracing the camera paths, we can see that we were able to look in those areas underneath the colony using just the top-down imagery alone. However, it is also important to note that a more complete imaging of occluded areas, such as the undersides of the branches, is not only more difficult and time-consuming, it imposes significant limitations on image and model quality, which is evident in the distortions of the branch tips, which were imaged with more oblique imagery. It is possible, it will just require more post-processing work after the image collection is complete. Okay, it is now time to move on from the images themselves to the other key pieces of information that you will need to collect as part of your large area imaging surveys. Structure for motion is the technology behind large area imaging, and it works without the need for any external inputs of scale or position. However, in order to be able to extract quantitative information, such as the size of corals, scale and orientation must be provided. Such information can be obtained in a variety of manners. Ultra-short baseline systems, known as USBL, and similar devices offer the promise of providing precise latitude and longitude, as well as depth measurements for each of the images we take underwater. In some cases, where an image collection involves many tens of thousands of images over very large areas, this information can be critical for model reconstruction and optimization procedures. Yet it is important to note, will also require significant effort in the form of post-processing. On the other hand, for image collections inside relatively smaller areas, diver-deployed scale bars and depth measurements can provide the scale and orientation information needed to extract precise quantitative information from larger imagery products, as well as also being adequate for model reconstruction and optimization procedures. It is important to note that even with scale, we don't know which way is up, so we need to make sure that we have this depth information. With this information in hand, we can establish the orientation of our plots with respect to the sea surface, which, for instance, is requisite for any study related to depth zonation. This information can be obtained with standard and easily fabricated equipment or with more sophisticated technologies. As always, your choice of approach should balance your research objectives with your resources. Finally, as we have noted previously, your need for geolocation will largely be dependent on your specific analyses. It is always required to have precise location information for each of your study sites. This is not only standard, but it will also be necessary for relocation in any repeat surveys later in time. However, if you are also interested in knowing how your community might be responding to physical forcings such as wave exposure, you will want your plot to be fully georeferenced, which requires multiple GPS points, or at a minimum, a GPS point and an accurate bearing between known objects in your model. If you have the resources, advanced tools such as USBLs are great options. Such information can be, as we said, such information can be used to improve the model reconstruction process. In some cases, though, so too can diver-deployed devices. Importantly, these tools require substantial financial, logistical, and intellectual investment, and thus their utility to your research should be considered before making any investment. Well, there we go. Over the next lectures, we're going to get into the details of everything we talked about today, but with this background knowledge in hand, I hope that you're ready to go out there and start your first large area imaging plan. Thank you.